In this video, we'll study forced oscillations. So I have already drawn the figure for this forced oscillations. So let us consider our usual spring mass damper system. So here we have the figure for the spring mass damper system. We have a spring of spring constant K that is being attached by mass M, and we have a damper with a damping constant B. Okay, so what is meant by forced oscillations? So this is basically what this is exactly similar to what we studied in the damped oscillations, except we have an external force which has certain amplitude and which is also periodic in nature. So look at this force. So this force is having magnitude, amplitude of F naught, and this sine function shows that this force is periodic in nature. What it means by periodic in nature? So this, if you look at the force properly, so this indicates this force initially as time proceeds at time t equal to 0, its magnitude is 0. So it will grow till F naught, again comes back to 0, reverses in direction, goes back to F naught, again comes to 0, and so on and so forth. So this force, which is external force, which is being applied on this mass M externally, this is periodic in nature. So what does it make difference to these oscillations? So let us study. So in damped oscillations, we just did the force balance for getting the differential equation for damped oscillations. In similar point of view, for the forced oscillations, we'll do the same. So let's do the force balance. So we have the inertial force, which is given by mass into acceleration. So this inertial force would be equals to, so this inertial force is basically the response by the system to the external forces being applied on it. So the first force, which is restoring force due to the spring with the spring constant K, it is given by minus Kx, because the spring will try to get that mass to the equilibrium position. So it is opposite to the displacement. It is given by minus Kx. So we have the force, resistive force due to that damping effect, which is given by minus Bv, where this V is velocity. And now, apart from these three forces which are being acted in case of damped oscillation, we have an additional force, which is kind of external force, which is periodic in nature, which is F naught times sine omega t. So look at this force again. So F naught is the amplitude of this forcing function, and omega is the frequency with which this force is being applied to the system. So let's do this and let's get the differential equation for the forced oscillations again. So again, this acceleration is second derivative. So this is m d2x over dt square, which is equal to minus kx minus b, velocity is dx by dt, and plus external periodic force F sine omega t. So let's get all this term to the same side of equation. So m d2x over dt square plus b dx over dt plus kx, and I'll keep this F naught, which is forcing term, F naught sine omega t, to the right hand side. So this is kind of similar to the damped oscillations. In damped oscillations, we didn't have this external force, which is periodic in nature. So in fact, we just saw the effect of damping on this natural frequency with which the system usually oscillates, right? So again, for the simplicity, we divided this differential equation by the mass. So we get d2x over dt square plus b over m times dx by dt plus k over m times x is equals to this amplitude F naught over m times sine omega t. And again, so we took certain terms like b upon m is like 2 times lambda, certain parameter, k over m, which is omega naught square. This omega naught is the natural frequency with which system oscillates in absence of damping, and other terms, let it be like that only. So I'll write the differential equation now. So let's write it. So it is d2x over dt square plus 2 lambda times dx by dt plus omega naught square times x is equals to this F naught over m times sine omega t. So this is exactly similar to the damped oscillations. But remember here, we on the right hand side, we have this periodic force which is being constantly applied to the system. And because of this system will oscillate with certain different frequency, which we saw in the damped oscillation, right? So now in the next part of this lecture, we'll discuss few points about solving this particular differential equation. Again, so this particular lecture is not focusing on the solution of the differential equation, rather will focus on the solution, the displacement solution, and not the procedure to get the solution, right? So briefly, we'll discuss the methodology to solve this particular differential equation. So let's discuss now. So now we have this differential equation. I'll write this again. So this is d2x over dt square plus 2 lambda times dx by dt plus omega naught square x is equals to f naught over m times sine omega t. Okay, so this differential equation in which we have the second derivative of x, first derivative of x, the x term itself, but we don't have a zero term on the right hand side. This differential equation is called non-homogeneous differential equation. And to solve the non-homogeneous differential equation, we need to consider two parts of the solution. So our solution for the displacement field x of t can be distinguished into two parts. xh, which is known as homogeneous solution as a function of t, plus xp as a function of t. xp is usually called particular solution, which depends on this forcing function on the right hand side. So what does it mean by homogeneous solution? So homogeneous solution is nothing but the solution of the differential equation which looks like a homogeneous differential equation. So what I mean by homogeneous again, so omega naught square x, this would be 0. So the solution of this differential equation, which is homogeneous, is known as homogeneous solution. Okay, and we have already seen how to get this solution of this particular differential equation. So we already know xh. Remember the nature. So as time progresses, I'll write this for you here. As time proceeds, this x will eventually, I'll write it as xh. This eventually will go to 0 because this is decay. This is decaying. And we have already seen this for the damped oscillations. I'll just brief the graph over here for the damped oscillation. So instead of writing now x of t, now I'm taking this as xh, homogeneous solution of t, and this is time t. So if you have this particular as an underdamped condition, so it will be like exponentially decaying function. This would be starting from minus a certain amplitude, decaying in nature, and our displacement will get oscillating between this. So our basically amplitude is decaying but oscillating at the same time. So this is underdamped. If you look for the overdamped system, so initially it will go to certain maximum value and then it will keep decreasing. It will keep decreasing slowly. Sorry for this. So it will not go to 0 and come back again. You can understand what I mean here. And if you look for the critically damped system, so it will also go in similar manner. To distinguish, I'll take it to the upper limit, and then it will slow down at the faster rate and it will eventually become 0. So what I want to emphasize here is as time progresses, all these amplitudes and all these displacements are becoming 0 or approaching to 0. So that's what we call it as a decaying displacement field, right? So we know this particular solution, and to find the particular solution, we have to use this forcing function itself. So particular solution depends on the forcing function. So if you see here, the forcing function is periodic in nature. So it is sine. So in general, for this sinusoidal forcing function, we take this particular solution in the form of a sine omega t plus b times cos of omega t. And if you put this particular equation into this governing differential equation, you'll find these constants a and b. So I'm not exactly doing mathematics to find these constants a and b, but I'm just dictating the procedure to solve this particular differential equation to get the particular solution. So if you put this xp as a sine omega t plus b cos omega t into this differential equation, you'll be able to find out the constants a and b. So how to find two constants from single equation? Remember, this function sine omega t and cos omega t are linearly independent, right? So what I mean by linearly independent, suppose if you have this particular condition, like you get something like this, a sine omega t plus b cos omega t equal to, let's say I got this as 2 sine omega t. Okay, so compare this sine omega t and cos omega t are being linearly independent. You can compare their coefficients separately. So comparing the coefficient of sine omega t, I get a equals to 2 and I get b equals to 0 here. So this is what I mean by linearly independent solution. So similar to this, if you put this xp in this differential equation, you'll end up with certain coefficient for this sine omega t and certain another coefficient for this cos omega t. And on the right hand side, you have this f0 over m. So if you compare the coefficient of sine omega t, you'll be able to figure out, and cos omega t coefficient is obviously 0. So you'll get two linear equations in A and B. And by solving those two linear equations for A and B, you'll be able to find out this particular solution. So I'll just write the solution, how it looks. So this xp of t, this looks like f0 over m divided by into the bracket. The first term is 2 lambda. Remember 2 lambda, this term, times omega. Omega is the frequency of this forcing function, and omega naught is the natural frequency of the system, right? So square of this plus into bracket omega naught minus omega bracket square. Sorry, omega naught square minus omega square bracket square, and the whole bracket raised to half, square root of this, times sine of omega t. Again, this omega is the frequency of this forcing function, minus there'll be some phase. There'll be some phase. Okay, so how I came from this sine and cosine together to get only sine. So you know this, right? So if you put this a as some sine of delta and b of some cos of delta, then using the trigonometry, basics of trigonometry, you can combine the angles omega t and delta, which we usually do in some superposition of waves and superposition of any two periodic functions, right? So this is what we get here. So this functions looks like this. Now, if I want to write this particular solution, x of t, which will look like xh of t, I'm purposefully not writing this solution here because we have already known this solution and we know the form of this solution. For your simplicity, I'll write this as xh of t. So this would be like let's say I'll call constant c1 e raised to alpha 1 times t plus c2 e raised to alpha 2 times t. This can be written as for overdamped solution, overdamped system. So if you have a critically damped system, you have c1 plus c2 times t multiplied by e to the power alpha t. In this case, alpha 1 and alpha 2 are same. So this is for critically damped system. This is for critically damped system. And if you have underdamped system, you have a complex solution. And if you write exponential of a complex number, you can write those terms in terms of sine and cosine. So you can write it c1 sine omega t plus c2 cos omega t, right? So this is the solution depending on different conditions, what we have already seen in the previous lecture. So this is for underdamped system. This is for underdamped system. All right. So now I'm not going to write this particular solution here, this homogeneous solution here. I'll just focus on this particular solution. So which will look like this. So xp of t. Now look at this solution here. This is very important. Now we want to understand the physics of this particular solution. So this xh, we have already drawn the graph for this. Now look at this xp. So xp is, this is some value. I'm not bothered about this value. Let's call this as a certain amplitude times sine of omega t minus delta. So what this indicates here? So this sign indicates that my displacement field, which is a particular solution, is periodic in nature with certain amplitude, And if I superimpose the solution of homogeneous differential equation xh, which is this particular graph, over this periodic function xp, I'll get the displacement field. So what does this mean again? Okay, this particular solution is sinusoidal, which is periodic in nature, which will be oscillating between amplitude plus a and minus a. And xh at the same time, it can oscillate or it cannot oscillate, but definitely as time progresses, it will decay to zero. Okay, so now understand this. So suppose our experiment started in which we have considered this forced oscillation. And now suppose as t progresses, as t progresses, this xh homogeneous solution, this is decaying in nature. So it is reducing, and is approaching to zero. But at the same time, my xp particular solution, as time proceeds, this is periodic in nature, so it will keep oscillating with same amplitude. It's not going to decay at all, right? So if I consider as time approaches to infinite, certain large time, what I mean by infinite is actually certain large time, then this xh will approach to zero because this is decaying in nature. And now what I remained with is x of t would be only xp of t. Now my system is oscillating with the displacement field x of t, which is only given by xp, particular solution of this differential equation. And this particular solution is again what? This is periodic in nature. So if I plot my displacement field here, okay, so this is time, this is x of t. So remember this condition. This is very important condition. As time t tends to infinite is as time progresses. Suppose if I consider this time here, by which this xh has now become zero, means like it's almost decayed all the amplitude, and now it has become almost zero. Now if I look for the time from here onwards, my solution will be looking like only this, which will be only oscillating with the same amplitude. Okay, so this solution is called steady state solution. This solution is called steady state. Why steady state? Because it is not going to decay at all. It will keep oscillating with the same amplitude, even though if I continue this experiment forever. So it will keep oscillating with the frequency equal to the forcing frequency omega. So look at this solution again, xp, the frequency of this solution. So this is periodic in nature, and this frequency omega is exactly same as the forcing frequency omega, right? So what did we understand here? So let me write this solution again. So I'll just erase everything and I'll write the brief solution here. Okay, so I'll write xp of t. xp of t will look like f naught over m divided by 2 lambda times omega square plus omega naught square minus omega square bracket square raised to half times sine of omega t minus certain phase delta. Now, as time tends to infinite, certain large value, our xh has now become almost equal to zero. And now x of t, our displacement, has approached to only particular solution. And if I look at this particular solution here, so I'm going to plot this here. So this is x of t. This is t. This is x of t. So to satisfy this particular condition, I'm assuming that at certain time t, my xh, so this is the time at which xh of t has almost become zero. So from here onwards, I don't have xh anymore. So my xt will exactly look like xp. And xp, if you compare this particular, so this is the nature, this is having the nature of a sine of omega t minus delta. So for the simplicity, I'll just plot the sinusoidal curve, sine of omega t. So it will keep oscillating like this. And this part of the solution is known as steady state solution. Steady state solution. All right. So it doesn't mean that we don't have the solution for this time, which is less than this particular time, right? So in this part of the solution, we have superposition of xh of t, and xp of t. So if I write xp of t, it will be again oscillating in nature with the same amplitude. And if I superimpose this xh homogeneous solution into this, which will be kind of either underdamped, overdamped, or critically damped. So in that it will be like looking like it will have certain amplitude. The xh will keep decreasing, and at the same time I'm superimposing this xp of t, which is periodic in nature, over this particular solution. So drawing this particular graph over here is quite critical, I would say, but it's not impossible. So you can have certain plotters like MATLAB and all, and you can plot these two solutions over here and add them up together and see how it looks like. But you'll definitely see that as time proceeds, at the higher times, the solution has now become only as this, which is periodic nature and without decaying its amplitude. So the initial part of the solution, this part of the solution is called transient solution. Transient solution. All right. So as my homogeneous amplitude decayed, the rest of the part, this particular is known as steady state, and the initial part of the solution, as time t tends to 0 and initial part of the solution, this is known as transient solution. All right. So now we have seen how the solution looks like. Now let's go a little deeper into this particular solution. So what happens? So look at this solution. What happens? Suppose my forcing frequency, look at this particular term here. Now, omega naught is entirely determined by the system itself, because we know this omega naught square is given by k over m. So we know the spring constant, we know the mass is being attached in the system. So the system's natural frequency omega naught is now fixed. Now, what we have here is omega, with which we are applying the periodic force on the system. Now, suppose if I take a case here, which case? In that case, my forcing frequency, the frequency of external force, external periodic force, which is being applied on the system, to be equal to natural frequency, omega equals to omega naught, natural frequency of this system. In that case, my particular solution would look like f naught over m again, divided by this term will vanish, and square root will go away. So I'll end up with only this times sine of omega t minus delta. So in short, I can write the amplitude of this periodic displacement equals to f naught over 2m lambda times omega. 2m lambda times omega. And if you look at this denominator, so look here. So for all other values of omega, which are other than omega naught, for this, as we are squaring this particular term, the minimum possible value for this term would be 0. And hence, the minimum value of this the denominator would be 2 times lambda times omega. So this amplitude is the maximum amplitude. Remember this thing. So if I take omega other than omega naught, this term will contribute. If this term contributes, my denominator increases. If my denominator increases, this amplitude will decrease. So the denominator to be minimum, this omega has to be equal to omega naught, which we considered here. And in such case, the denominator being minimum, this amplitude will be maximum. So I can say here that maximum amplitude is given by f naught over 2m lambda times omega. And this condition in which the system oscillates with the maximum amplitude is called resonance. This particular condition is called resonance. So in short, in a nutshell, when the force in a system of forced vibrations, if the forcing function, the frequency of forcing function is equal to the natural frequency of the system, then system will start vibrating or oscillating with the maximum amplitude, and such condition is known as a resonance. And in resonance, system oscillates with the maximum amplitude. So this is the maximum possible amplitude. Now, going beyond this, now suppose if I don't have the damper, again, within this case itself, so let's say call this case A, this is the first one, this is the second one. So within this case itself means I have omega, forcing frequency equal to natural frequency, and if I don't have damper, so what I mean by I don't have damper, so this is like I just have this spring mass system. Let's say this is a spring and this is some mass, and I have no damper, and now I'm applying certain periodic force on this with F naught sine omega t. So what will happen here? K, and this is M. So for omega equals to omega naught, I have this maximum. So in this case, A would be, oh, sorry, what would be A amplitude of this particular vibrations? Look at this particular expression. So omega is omega naught, so this term is going to vanish. Now lambda is what? Lambda is B over 2m. So my B damping is 0, that's why lambda will be 0. If my lambda is 0, the denominator will vanish. So denominator becomes 0, and now this amplitude tends to infinite. What is meant by amplitude is now becoming infinite. This is disaster. This is disaster, that you cannot control the amplitude of these vibrations, and it will oscillate with the maximum possible amplitude the system will oscillate with. But remember, this is a very hypothetical case. So what is meant by having damping equal to 0? Damping is what? Damping is basically a resistive force. And in practice, in nature, we cannot eliminate any kind of resistive force. Look at the examples nearby you. Suppose if you, even if you consider the example of simple pendulum, though if you don't feel any resistive kind of force, but there is air, and if your body is moving in air, during the motion, air is going to oppose it through air drag. Suppose if your body is flowing through certain fluid, your body will be feeling certain kind of viscous drag, which is resistive, right? So you cannot eliminate the damping or the resistive force in practice or in nature. So that's why we are not worrying about this B equal to 0 condition. So in reality, in practice, our amplitude will never shoot to infinite value. But for certain small dampings, it will definitely shoot up. So let's discuss this. Now we are not bothered about this B equal to 0 condition. So we'll never take this B equal to 0. So only take this particular resonant condition here, in which my system is vibrating, the forcing function has the frequency equal to the natural frequency of the system. So in that case, so when omega, forcing frequency equals to omega naught, so that is resonant frequency. Let me call as a resonant frequency. So in that case, my maximum amplitude is given by F naught over 2m lambda times omega, right? So this is the maximum amplitude. Now suppose if I plot this particular graph, so if I take different values of forcing frequency, this is forcing frequency, and let's take amplitude here. Okay, all right. For certain frequency where this omega becomes equal to omega naught, my amplitude will be maximum. My amplitude will be maximum. So if I look at the graph here, so if omega is equal to 0, so I'm applying a constant force. So I'll be having certain frequency, certain amplitude. So this amplitude will start growing till the system is being applied with the force with the frequency equal to the natural frequency. So at this condition, my amplitude will be maximum. And again, it will, if you still go for the higher frequencies, and again it will start decreasing, decreasing. So this graph will look like a normal distribution with the maximum value of amplitude occurring at omega equals to omega naught, natural frequency. Okay, all right. Now, within this experiment, suppose if I change the value of B, the damping factor. Now, suppose if I increase this B parameter, what it means by? So basically, I'm increasing the damping effect. So if I increase B, then this lambda is given by B over 2m. This is also going to increase. And if lambda increases, this A max will decrease. So for higher damping, I'll get lesser amplitudes. Okay, so if I increase this damping more, I'm able to now reach till this only. Again, I'll come back to this. Now, suppose what happens if I decrease B? So I am reducing the damping effect. So if I reduce the damping, what actually damping does? Damping helps to decay the amplitude. So now there is no damping. Suppose there is a less damping. So system will try to oscillate with even higher amplitude. So it will shoot up again. Sorry for the nature of the graph, but try to understand what I actually mean here. Okay, so this is for less value of B. This is for high value of B, and this graph is for moderate value of B. So in short, if I keep on decreasing the damping factor, my graph will shift upwards. The amplitude, the maximum amplitude with which system will oscillate will even increase further, right? So this is what the graph looks like. So this graph you should be able to understand. All right. So if you make it 0, so it will entirely shoot up and go to infinity, but which is not practical. So we are not bothered about it. In fact, in practical, we have certain minimum value of B all the time. So system will oscillate with certain finite amplitude only. Okay, so far we have now discussed the forced vibrations. Now, going a little beyond from this, we'll just discuss the sharpness of resonance. What is meant by sharpness of resonance? Now, you see here, there is a damping, means like there is a power dissipation in the system. Damping means kind of resistive force. And if there is a resistive force, your energy is going to decay. The simplest example, if you take, suppose if you are riding a cycle on a plain horizontal road, if you pedal and if you stop pedaling now, what happens? Now, the ground is offering a kind of resistive force on your bicycle. And due to this opposing force, the energy what you put in the bicycle for moving it is now going to decrease due to this resistive force. And it will keep decreasing at it, and eventually it will become 0, where your bicycle will stop moving. So this is what happens here. So damping provides a resistive force. So your system is going to dissipate energy, keep on dissipating energy, and finally it will dissipate the entire energy and comes back to the stable position, what we call as an equilibrium position, right? So, all right. So what is meant by sharpness of the resonance? So it looks like, so if I suppose if I take this particular graph again, this A, this is omega. Suppose if I take certain value of B, so it will shoot up and again come back. Now, for this particular maximum A max, maximum amplitude, there is certain power dissipation. Now, corresponding to this, let's call this as P max. This is power. This is maximum power dissipation corresponding to the maximum amplitude achieved by the system at resonant frequency. Okay, now I'm going to consider power which is half of maximum power. So it will be something like this, somewhere here. Okay, so there must be certain amplitude corresponding to half of the maximum power. So similar to that. So for P max, there is an amplitude. So I could say that for maximum amplitude, there is certain maximum dissipative power. So similarly, for certain amplitude, the power corresponding to this particular amplitude will be half of the maximum. So if I take this amplitude for which the power corresponding to this amplitude is half of the maximum, and if I take this particular values, so I get certain two frequencies. So these are the two frequencies for which the power dissipated in the system is half of the maximum power which is being dissipated by the system. So these frequencies are called half power points. So let's say this is omega 1. This is first one. And remember, this would be on either sides of the resonant frequency, no doubt about it, because this graph of A versus omega is kind of normal distribution in which it is approaching to maximum at resonant frequency omega naught. So this omega 1 and omega 2 are the frequencies for which the power dissipated by system is half of the maximum power that is being dissipated by the system. So the difference between these two frequencies, omega 2 minus omega 1, is called bandwidth. Okay. And if the bandwidth is less, so let me write it here. If the bandwidth is less, so what it indicates, and what it indicates when bandwidth is more. So let us try to figure this out again with the help of graph only. If I take this particular graph, high, maximum, come back like this. Suppose if I take similar graph, okay, let me choose another color for this. All right. So if I take similar graph like this, approaches to same maximum amplitude, and now coming back. All right. So these are two different graphs. Okay, now suppose this is the half of the maximum power. And if I take corresponding frequencies, for the black color graph, this is the bandwidth. And for the red one, this is the bandwidth. So let me write this down. This is the frequency omega 1B. And this is the frequency omega 2B. So B for black. And this is the omega 1R. R for red. This is the omega 2R. R for red. So bandwidth. So bandwidth for black is omega 2B minus omega 1B. And bandwidth for red is omega 2R minus omega 1R. So from this, you'll be able to figure out that bandwidth of black is less than bandwidth of red. So red means I just drawn the graph by red. That's why I'm referring these colors only. All right. Okay. So now look at these figures, right? So which is more sharper? So if you look at the red graph and black graph, definitely the black one is more sharper. So sharp is black. So black is more sharper. So what does it mean? So I can relate the bandwidth to the sharpness of the resonance itself. Look at this. The bandwidth of the black is less, but the sharpness is more. So what does it mean? If my bandwidth is less, it is more sharp. You can say the sharper. And if my bandwidth is more, it is less sharp. It is less sharp. Okay, so now we have studied this particular, the sharpness of the resonance. And it can be sometimes it can be this behavior, whatever we have studied is kind of qualitative behavior, right? So bandwidth is more, it is less sharp, bandwidth is less, it is more sharp, but how sharp and how less sharp, right? So this can be quantized like by using this Q factor. You must have studied in some electrostatic part or AC currents, AC circuits with series LCR circuit and all, Q factor. So this Q factor is nothing but omega naught, which is a natural frequency, and bandwidth. All right, so by this ratio, if your bandwidth is less, this Q factor will be more and sharpness will be more. So now you are able to quantify the sharpness of the resonance through this Q factor. So for certain resonant curve, if your Q factor is higher, it means that your resonance is more sharp. And if your Q factor is smaller, it means that your resonance is not sharp, it's less sharp, right? So it is kind of distributed more over this. And this, the first one curve is kind of less distributed, looks like more sharp. All right, then. This is how we completed the forced oscillations, in which we have studied. Briefly, we have discussed the solution methodology to solve non-homogeneous differential equation in this particular forced vibrations, forced oscillations, and it has two solutions. It is comprised of two solutions. One is homogeneous solution and another is particular solution. Then we looked at steady state solution and transient solution. Now, particularly, if we focused on the steady state solution and saw that at certain frequency of forced vibration, the forcing function, our amplitude is becoming maximum, and that frequency is nothing but the natural frequency of the system. So when my forcing function is having frequency equal to the natural frequency of the system, my system is going to vibrate with the maximum amplitude possible. And this particular condition is called resonance. And within this condition, if I don't have the damping at all, so my amplitude will shoot up to infinity. But in practice, we never have this B to be equal to 0. So we are not bothered about that. So we'll have certain maximum amplitude which is finite in value, right? So all right, then, depending on this, based on this particular forced vibration, in the next lecture, we'll discuss and we'll compare these forced oscillations with series LCR circuit in AC current with AC source. All right, then, let's meet in the next lecture.